we start. All right, everyone. Let's start the afternoon session with Sai, and he talks about virtual channel purification. Let's give it away.
Okay, everyone, can you hear me fine? Yeah, okay. So welcome to the afternoon session. And in this session, for the first talk, I'm going to talk about virtual channel purification. So this is a joint work with Zhenhuan Liu, Xingjian Zhang, and also Yueyang Fei. And Zhenhuan is also here in the conference. He did most of the hard work in this work. So if you have any further question, you can either approach me or approach him. Yeah. So overall, in this talk, I'm going to talk to you about mostly two things. So first of all, I'm going to introduce a powerful quantum error mitigation scheme with a minimal set of assumptions. And in the second part of it, I'm going to talk about some possible integration between quantum error mitigation and quantum error correction. So I guess this is kind of like the first talk that kind of mentioned about quantum error mitigation, if I'm not mistaken. So I'm going to try to motivate and explain quantum error mitigation a bit. So in the conventional way to implement QEC, at least those codes that various experimental groups are actively trying to actually implement right now, they still tend to have a fair bit of qubit overhead. And usually they have quite high requirement of gates, like it need high gate fidelity of like at least like 1% error rate or so. And also, the logical case when you try to implement on the encoded qubit can be slow compared to the physical operation. So to address this and to try to better utilize the quantum hardware that we already have, quantum error mitigation is another way to try to tackle noise. So the essential idea is to use additional number of circuit runs in order to reduce the bias into output statistic using post-processing. So you can essentially look at the picture here, where the horizontal axis is the possible output values from the circuit, while the vertical axis is the probability of that particular output value. So let's say the ideal expectation value is this red dot here, red point here. Then the noise actually it will shift. Noise will shift the expectation value to this particular orange point, which deviates quite a lot, and the output distribution is signaled by this orange curve here. Well, what error mitigation try to achieve is to essentially move the expectation value much closer to the ideal value. And by doing so, actually in the process will inevitably broaden this distribution And this will also lead to more number of circuit runs needed compared to the original one, because the need of reducing the variance of this distribution, and thus the overhead of circuit runs here. But the advantage that it brings is essentially it requires no or low qubit overhead because it's mostly post-processing. And it also very few additional gates needed. So there is really like very low or no requirement on the gate fidelity in order to be able to remove noise. And furthermore, you usually are computing on the raw physical qubit or like codes of very low distance, because if it's very high distance, then all of your error are dealt with by TQC anyway. So this usually means faster gates. So I have a talk about the motivation of QEM. So existing QEM methods, most of them require a various sets of assumptions. For example, you require either like noise knowledge or the ability to tune the noise, or some known symmetry on the output state, known symmetry of the problem, or some restriction on the target state and target problem. So what we're trying to do is trying to remove all of this restriction, because all of this assumption will limit the application scenario and make it very hard for experimentalists to choose the right techniques to apply. So we're going to introduce a new technique that removes all of the assumptions mentioned here. So the way it goes is we will first introduce existing techniques called virtual state purification. So this is work by Alan Kozel in Oxford and also Bill Huggins in Google. And what they do is they assume that the ideal output is some pure state, right? We denote as rho 0 here. And then the actual noisy output is actually this rho 0 with some error component rho e. And we assume there is just one error component orthogonal to rho 0 here for simplicity, but the scheme goes more general than that. So what the purification process essentially try to do is it try to prepare this purified state, which is essentially proportional to rho to the power of n. And what this will do is if p is small, it will suppress p from p to n, which is exponential in the degree of purification n, right? So this is all well and good. It seems like very powerful noise suppression has been achieved, but how do we exactly achieve these states here? So the insights they give is instead of physically prepare this purified state, what you can do is actually very often experimenting in a lot of problems, you're actually trying to measure an observable on this state instead. You're not just trying to produce the state itself. And to obtain this expectation value, it can actually be written and obtained using this circuit here. So what this circuit is essentially use n copies of the noisy state rho. And then here there is a control qubit with a control permutation operator. So this will permute all the copies, so control permutation between the copies. And what this circuit will essentially enable you to do is measuring x and o will form the denominator here, and then measuring x will form the numerator here, and taking the quotient of them will give you the purified expectation value you want. So this is all well and good, but it comes with some restrictions, so to speak. So it's good that it can suppress error exponentially with the number of copies of rho here, right? But its limitation is its ideal output state have to be a pure state. So its input output state have to be a pure state. And second of all, the noise should be small such that the error-free component remains the dominant component, because as you see here, if 1 minus p is small instead, then 1 minus p will be suppressed more than the p. Okay, so it's a great technique, but still come with some assumptions. So how do we overcome this? This can be actually achieved by purifying the channel instead of purifying the state itself. So what do I mean by that is, let's say we have an error channel with 1 minus p probability of no error happening and p probability of some error component happening. So instead of purifying the noisy state, we're going to obtain a purified channel in the same spirit, where the coefficient the error coefficient is suppressed from p to p to the n, right? Again, it's exponentially n. And the circuit that we are trying to achieve this is quite similar to before. So it's just this circuit here, and exactly the same as before. Instead of trying to physically prepare the purified channel, we're just trying to obtain the expectation value obtained as a result of this purified channel. And we're using this circuit here. So the main difference compared to before is, instead of one control permutation, we're now using two that trying to bracket sandwich these copies of a noise channel inside. And then for the ancillary input, we're no longer using the same input as the main register. And what we need is simply maximally mixed state input for the ancillary qubit, which can be just prepared by random initialization. So it's much easier to prepare. And so this seems like it's just a simple modification of before, but what it enables you to do is now it enables you to purify the channel instead of the state. And the first advantage, obviously bring, is it does not require rho naught to be pure anymore. We're purifying the channel, so all we need is to say that the ideal channel is a unitary, which is often the case. Very often in the experiment, the ideal kind of thing we want to implement is some kind of unitary. And second of all, if you look at before, if you have many layers of gates, then the state purification side of things, it can only do one purification step at the end to purify the whole noisy state at one go. But if you are purifying the channels, you can actually do it layer by layer, one by one. And this actually enables you to remove the errors as it goes, so to prevent error accumulation, which can increase your power of error suppression by quite a bit. And furthermore, if you look at this circuit here, so the full circuit have some error rate p. If p is large, as we say before, this thing does not work anymore. I mean, if p is larger than the identity component, than the error-free component. But if you look at this here, we can subdivide our circuit until there is enough layer such that the error rate within each layer is low enough to be able to achieve a purification. So we can almost always being able to implement channel purification. So this restriction on the error rate is also removed. So with all of this restriction removed, actually we have achieved one of the quantum error mitigation techniques that do not require any of the assumption below. It do not require knowledge of the gate model. It do not require any constraints on the input-output state, and it do not require any knowledge of the target problem. And it still offers the rigorous performance guarantee of a p suppressing p to the n, as we mentioned before. So another additional advantage. So I have already mentioned by implementing layer by layer, you can remove more error because you prevent error accumulation. Another example that is more powerful than before is if you look at the specific example of globally depolarizing noise. So we haven't talked about multiple error component before, but if your error component is smaller, right? Because you're suppressing from p to the n, if you have smaller p, it means you have a stronger suppression. A more error component means that you have a smaller p, right? So more error component means stronger suppression. If you look at global depolarizing noise, it has 4 to the n number of Pauli error components. While if you look at the state, the maximally mixed state, you only have 2 to the n Pauli components. So the channel variance have exponentially more error component than the state variant. This also means that for the particular example of globally depolarizing noise, channel purification can actually achieve exponentially stronger suppression than its state counterpart. Okay, so this is all I want to talk about the purification, virtual channel purification part. And the next question we want to answer is how to actually integrate QEC and QEM. So because both of these, because as you know, noise are one of the is the constraint of building a quantum computer. So we just want to throw everything we have to it until it can no longer suppress the error anymore. So for the foreseeable future, we definitely want to implement QEM and QEC and all the other possible error suppression techniques together in order to push the error rate as low as possible. That's why this is a very interesting and important direction to explore. And what people have done before is mostly put QEM on top of QEC. So what that means is, okay, we don't have the resources, don't have enough low gate error rate or enough number of qubits in order to be able to achieve low enough logical error rate. So for the remaining logical errors, we're just going to perform quantum error mitigation at a logical level to suppress that. And that has led to some very interesting work from IBM and also NTT. But this kind of method is mostly kind of like viewing QEM and QEC separately without much synergy. So we want something that is like more integrated, so to speak, and maybe provide us with some kind of perspective on, is there some kind of more general framework going on there? So we will try to provide such an example. And before that, let's look back at this circuit that we just looked at before. This is a 2-copy version of the channel purification, right? And if you look at this circuit, the weirdest things here is that we are inputting a maximally mixed state here in order to mitigate errors, right? While maximally mixed state is supposedly the noisiest state. So it's a bit counterintuitive here. And you must think, is there something else we can do there to make this protocol better? So we look at that. So if you input this with some general state sigma instead, and you do the math of performing the measurement of X, but not performing the measurement of O first, so just performing a measurement of X. After this X measurement and doing the post-processing, the effective output state before measuring O is this thing here. So what this thing here is you can see that EJ is acting on one side while EI is acting on the other. EJ is from one of the channel while EI is from the other channel. So what this enables you to achieve is some kind of virtual entanglement between these two channels. So these two noise channels are virtually entangled via this circuit here. So if you look at this, what it enables you to achieve, what enables you to achieve is if you choose this to be a code state of a quantum error correction code that can correct all of the noise in this particular error channel according to the KO condition, then we can actually achieve the same effect as regular virtual channel purification. So this is not very interesting because you go through all the trouble of preparing a code state, but what you can achieve is still the same effect as the maximally mixed state. But what is more interesting is now you can actually try to perform syndrome measurement, right? And the result of this syndrome measurement is actually will collapse the noise of one particular channel. But because these two channels are entangled, actually this syndrome measurement will collapse the noise into the particular syndrome subspace of both channels on both registers. So what it enables you to do is actually by performing syndrome here, you collapse the noise on this register and enable you to actually perform correction on the second register, which is unencoded. So this can actually enable you to remove all of the noise on the main register compared to just purifying it. And what it enables you to do, this with just 2 copy and only paying the price of like purification instead of the price needed to like remove all of the noise. By price, I mean the sampling cost. Okay, so this is far more interesting now. And this is, as you see, is a very integrated way of integrating QEM and QEC. It's not just putting QEM on top of QEC. The last kind of things that I want to say is this particular circuit here is a newer thing that we just added onto archive maybe 3 weeks ago. And what this picture here is instead of 1 error channel, we have 2 error channel E and F. And here the E and F are the blip flip channel and the phase flip channel. So we are not just want to correct 1 channel, we want to correct both blip flip and phase flip channel. And what we do is we input a blip flip code on 1 register and a phase flip code on the other register. And because of, again, these 2 error channels, these error channels on the 2 register are entangled, what it enables you to do is by checking the blip flip noise and the phase flip noise, we can actually collapse the blip flip and phase flip noise on the 2nd register, and we can correct them on the 2nd register. So in this way, we can actually, by inputting just a blip flip and phase flip code, we correct both kind of noise on 1 of the register, achieving what can only be done by surface code before. So I will just preempt one of the questions that were about to be asked here. The noise on different registers do not have to be exactly the same. They can be different, but I will not go into the details. And I would just want to go with the summary here. So what we do is we have introduced QEM techniques that require almost no assumption, that have very wide applicability. It also has enhanced flexibility because it can target particular gate layer or particular gates. And it has stronger error suppression compared to before. And it also has very native integration with quantum error correction, enable us to go beyond the usual kind of bias variance trade-off. So enable us to go beyond its original error suppression power without increasing the sampling noise at sampling cost. And it enables the virtual entanglement of different noise elements that enable us to merge kind of the error correction power of different registers. And I think this is a very interesting direction to explore. So with that, thank you.
Are there any questions? Yeah, here.
Thank you for the nice talk. I have a question on the sampling cost of this method. Especially you claim that by using a virtual channel purification instead of a state purification, you can achieve exponential error suppression. How say exponentially, let's say larger error suppression over the state purification version. So is the sampling cost the same as the state purification if you want to achieve the 4 to n suppression?
No. So if you're just using
sorry, I mean the I agree with this error suppression rate, but
yeah, I know what you mean. Yeah, the sampling cost, right? Yeah, you are right. So essentially, if you are doing just pure QEM, right? I mean, different QEM methods does have slightly different scaling, but like I say, the general rule is the more errors you want to remove, right, the more sampling costs you won't need to pay. So in the case of specific comparison between VSP and VCP state and the channel version, VSP already suppressed the noise to quite a low level. Let's say like, okay, it suppresses circuit noise to like 0.01 noise per circuit run and things like that. So VCP can take this further, and the cost will be comparable because it's suppressing very small noise to an extremely small noise. So the increase in sampling cost is small because the additional noise you're suppressing, the magnitude is small.
Yes, so you mean...
So there will be more sampling cost, but
kind
of comparable because the VSP is removing all of the, almost all of the noise anyway.
Okay, thank you.
Yeah.
Is there maybe one more quick? Oh, yeah.
Thank you for a very interesting talk. I just want to make sure in what regime your channel virtual channel purification will be useful. I mean, like you said that like you can get purify your channel at each layer, but the assumption we need to do that is that the error rate of how to say in each layer should be quite large compared to the control swap gate.
Yeah.
But like in this regime, like control swap gate may be very noisy, and in early fault tolerant regime, I think control swap gate is not a clipboard operator, so it may also be noisy. So I want to know in what regime will it be useful?
Yeah, I think this is a very good question. So in like you say, in this regime, maybe the layer can go smaller, but in fault tolerant regime, each layer may need to go a bit deeper such that it's the error rate of each layer, as you say, need to be larger than the control swap. But because as you say, in fault tolerant regime, the control swap probably need to be implemented by CCZ and things like that. So you have more calls. So you need to do a trade-off there, which means that, okay, maybe you want to have the layer larger, or even the whole circuit is a layer. But even if the whole circuit is just one layer, you'll still do better than simply doing state purification.
So you mean that you do virtual channel purification in the whole layer? Yeah,
you can do the whole circuit as a layer, or you can you can just adjust the depth of your layer as you wish. Depends on what is the error rate of your individual gates in the circuit, and also the cost for implementing the control swap.
Yeah, thank you very much.
Let's maybe have more questions offline and thank the speaker once again.
Yeah. Oh, yeah. Yes. Change a lot. You didn't. Oh, yes. Yeah. I was in this. I mean, when I met you, I guess. Same face, shorter hair. Yeah. Maybe additional 1 year. Yeah, so you eventually moved to Okinawa. You wanted to. Yeah.
Let's start with the last talk of the session by Bo Young. We'll talk about quantum error suppression with subgroup stabilization.
Thank you for your introduction. I'm Boyan, giving a talk on the quantum error suppression with subgroup stabilization, which is the joint work with Elham Kachefi, Dominique Laito, and Olivier. So yeah, Dominique's over there. So yeah, and thanks to the talk by Zhenyu, I guess I don't have to explain much about quantum error mitigation, but yeah, the idea is very similar to the Zhenyu's talk. So our contribution in a sentence will be that we design the quantum state purification with taking m noisy input and output m purified outputs using order of log m ancillary qubit and order of log m steps of permutation operation controlled by each ancillary. So this will quadratically suppress the error probability p to p square, and it will, if you apply this gadget repeatedly, you can suppress the either coherent or stochastic errors to linearly smaller to the number of copies. And then, yeah, we actually reduce the circuit implementation cost from the previous work, which adopts the same idea as state purification, stabilization of the M copies. Yeah, so the implementation cost is drastically reduced from the previous paper. And yeah, so this work is can be seen as kind of a beyond quantum error mitigation because we are targeting to purify the quantum, reduce the noise in the quantum states instead of expectation value, which is addressed by the quantum error mitigation mainly. Yeah, so yes, because in this sense we can also do some error suppression when we try to solve the sampling problems. And then the implementation cost of our method is kind of before the fault tolerance and way a little bit more heavier than the near-term scheme. So so the quantum state purification in this context is to exploit the redundancy of the symmetry over multiple noisy inputs by post-selecting somehow the symmetric subspace. So this idea is firstly proposed by very the paper long time ago. Yeah, so it is to stabilize m copies into the symmetric subspace using the symmetric group, and we basically refer to this idea and make the circuit implementation of this method lighter than the previous one. Yeah, and actually this stabilization method is also inspiring somehow the purification-based method, which is also referred to as virtual state purification in Zhenyu's talk, essentially to compute the error mitigated expectation value by computing the trace of higher degrees of powers of density matrix. And in our proposed method, we also showed a optimality of the sampling costs in terms of expected number of copies we have to pay to achieve to obtain the purified quantum state. So we use somehow the works in the context of the state purification in terms of fidelity, optimal fidelity. Yeah, especially this recursive purification of high dimensional state. Okay, so for the very simple case of state purification by stabilization, we can take the swap test, or in different words, swap gadget as an example. So if you see, if you assume that the noisy state rho can be spectral decomposed in this way, so it is a classical mixture of each eigen vectors with eigenstate, which eigenstates are sorted in descending order. Then you can obtain this purified, kind of slightly purified quantum states as an output, taking the form of linear combination of original noisy quantum state and the square of the original noisy state. So this square, as Jenny thought, will suppress the submissive eigenvectors and amplify the contribution of the dominant eigenvector. Then you can see that the linear combination of rho and rho square will kind of increase the purity of the quantum state. So generalizing this idea, as I mentioned, this very old paper by Baranko et al. Project m inputs instead of 2 to their symmetric subspace, designed by the associated with symmetric subspace, symmetric group. So they project m copies of noisy inputs into permutation invariant subspace. So for example, the symmetric the basis of a symmetric subspace of 3 copies will be like this. Then you can see that each copies of each basis this each register has permutation invariance in it. Sorry, okay, this one is additional. Sorry, it's a typo. And they assume their gadgets can be used as a repetitive, kind of this in this repetitive way. So in a short time evolution delta t. So if you use n step and in each step with delta t time evolution followed by this state verification gadget, you can actually keep the exponential decaying errors small enough at the end, because for example, if you take polynomial number of copies here, then without this state verification, the error, the success probability of obtain the pure state this can be approximated in this quantity. But if this state verification gadget can suppress the errors into a 1/m scale, then this with this gadget, so the error will be kept in exponentially smaller to this level. But the implementation cost of this gadget is relatively huge, because you have to pay m log m of ancillary qubits, and especially this unitary U here is to create the uniformly uniform superposition of each quantum state. So if if m factorial here is not 2 to m, then you have to essentially do the quantum Fourier transformation, which also takes kind of this m log m square of control swap gates. And then here each you also have to apply order of m log m permutation operation. So this will also increase the number of swap gates inside. Not swap, I mean the 2 qubit gates. So yeah, it doesn't in terms of implementation cost, it's not really good for before the tutorial. So here we propose the cyclic group gadget, which is to map the m noisy inputs into the rotation invariant subspace by using the the cyclic group CM here. So the project is modified from this this projector to this one. Then then the circuit overhead will be decrease from order of log m log m qubits to just log m qubits, and the required permutation operation here will also be reduced into just log m steps. Yeah. So if you see the repetitive application of either a symmetric group gadget and a cyclic group gadget, we see these two have the same purification performance under the short time evolution with this noisy state. So the idea is that under the short time evolution, you can take the first order of the delta t, then the error is also just includes this the first order contribution of delta t. So if you apply the gadget of even the cyclic group gadget, you can suppress the error into 1 over m by factor of 1 over m. Yeah, compared to the without any error suppression. And for the stochastic errors, you can also assume that the noisy state as the linear combination of the pure state and the trace-free Hamiltonian sigma k. And if you take the first order of this approximation of this sigma, then you can just consider take this part into account. You don't have to take this part. So then you can also see that the fidelity and the purity are, let's say, kind of modified or improved in terms of this by factor of 1 over m. So yeah. So we can also consider the single round application of our proposed method. I'm giving an example with 8 copies here. So the circuit implementation of this 8 copies model is can be specifically drew down in this case. So yeah, you just do the, let's say, local hard mode gate and then apply log m of times of permutation, which is 3 here. And then actually the project here is specifically can be written down as this form, which is the linear combination, equally linear combination of the project of the permutation operation. So each corresponds to this kind of operation. Then what you obtain as output states is, it's a linear combination of a row, original row, and linearly amplified. Sorry, let's say, the higher degrees of row with linearly amplified coefficients. So in this case, you can see that yeah, our gadgets can let's say suppress or suppress the noise also linearly. Well, actually, ideally, I can finish my talk here, but the world is very cruel. That this row to 8, for example, row to m anyway, would not only amplified the dominant eigenvector exponentially larger, but will also suppress, let's say, the global, let's say, amplitude exponentially smaller. So the contribution of this part is not that big as these 4 are written here. And then this means you will see somehow the balance points because the contribution of amplification of row to 8 through the coefficient is linearly growing to the number of copies m. But here, the contribution of row to m part will decrease exponentially to m. So you'll see some balance point of the purified state. And this is the numerical simulation. Well, you can see that at some point, if you increase the number of copies, okay, this is for the depolarized input, but the purification rate p tilde over p will go back to the original noisy level, let's say noise level. So you can clearly see somehow the balance point here. But you can still see that, okay, it is very unlikely that you use 1,000 of copies in this gadget. So just use 10 qubit, then 10 copies, then the error scaling is still linearly scaling, which is good, still good, somehow fits a certain purpose of our usage. Yeah, and it also seems that the maximal let's say purification point, this balance point, will suppress the error into from p to p square, which is actually true also from the theory. So we show that for the balance point here, the m will be 1 minus 1 over log 1 minus p. And using this number of copies, you will achieve the optimal, sorry, the maximally, how to say, suppressed error probability p, let's say p star in this form. And if you assume that p is small enough, then the p star will be can be approximated as EP square. So it's a quadratical error suppression. And to achieve this quadratical error suppression, you have to pay order of p 1 over p sampling, how to say, number of copies. This is also optimal by reasoning or comparing the sampling cost of our method and the recursive application of swap gadget, where they show the optimality of in terms of sampling cost. So in this sense, we can claim that by the, how to say, dominant factor, we can claim that the sampling cost of our method is optimal. So finally, we compare the implementation cost and the purification rate of each method. So you can see that in the very first work of symmetric group gadget, they use the projection in terms of a symmetric group to achieve a purification rate of 1 over m with m purified output. But it uses m log m order of ancillary qubit and further more controlled swap gates. And actually, you may think this error suppression by derangement circuit, the virtual state purification method, just uses a single ancillary qubit and the linear scaling of controlled swap gates, but it doesn't help suppressing the errors in the quantum state. But it's rather to suppress the error in the expectation value, which is different from our our goal. And this recursive application of swap gadget, they also seem to achieve somehow lighter implementation, but they just give 2 outputs. So it doesn't help, how to say, it doesn't fit the repetitive application of this purification gadget. Yeah. So in this sense, our proposal can be seen as a kind of sweet spot, taking all of them, taking all of the advantage of their methods. So yeah, it's a really nicely balanced method, which can be, how to say, run on the earliest TQC scheme. And yeah, of course, the overhead, if you see from here, from the error mitigation method, it's only the log m overhead. Okay, so as a future application, of course, you can consider, combining the cyclic group gadget with the error correction code, but we can also address the problem of, how to say, robust quantum verification protocol, especially when you assume that the future, how to say, quantum ecosystem is very likely to have the quantumly limited client on the server. So in this scenario, you may want to, say, verify the correctness or the blindness of the computation against server. So this problem is well studied by previous works, but it's not really, how to say, well studied. Oh, sorry, well studied for the sampling problems. So this is one direction, and the other direction can be the combination of the virtual channel purification. Which is given by Zhenyu in the previous talk. So yeah, just take home message. We designed a cyclic group gadget which will suppress the error rate p to its quadratical order with the inverse, like linear sample, which is also shown as optimal. And so the circuit implementation cost is drastically reduced from the previous work, and also it's just log m times larger than the purification-based quantum verification method. Finally, we analyzed which part is influential in the in suppressing the error from the quantum states instead of expectation value. Yeah, that's it. Thank you for your attention, and I'm just turned to the third year of PhD, so I'm kind of looking for a postdoc position. So please feel free to talk to me. Yeah, thank you.
Thanks a lot. Are there any questions in the room?
Thank you for a very interesting talk. I want to ask about sampling overhead compared to the virtual purification. I mean the quantum error mitigation method. In some work, they say that when we want to purify, when we want to mitigate errors on quantum state itself, not at the expectation value level, we need to spend exponentially more sampling overhead in terms of qubit count. But so in your work, is there any qubit count dependence on your sampling overhead, or it does not matter?
Yes, thank you for your question. It's a really nice point. Actually, I didn't really mention this figure actually, but this figure says that if you increase the dimension of the quantum states, it will converge to a certain, this curve, red curve, right? So, well, we can see that, even for the infinite dimension of the quantum states, or the finite dimension, which is very close to infinite, it's still scaling with inverse polynomial. Inverse the 1 over p for the sampling cost, because this discussion holds for the infinite dimension of the quantum state. So yeah, hope this makes sense.
Thank you very much.
Thank you.
Any other question? Yeah.
Yes, you're right. You mean we can do the same stuff as this recursive application, or is it what you want to do?
Yeah.
Okay, good. Yeah, it's possible, but you have to consume kind of exponential cost. Yeah, well, you can optimize that. You don't have to pay exponentially, many copies actually. But we didn't really analyze that because it's kind of a little bit complicated and trivial. So, but essentially, it's possible. Yeah. Thank you.
Okay, thank you for the nice talk. So the control permutation operations that you need to implement the gadget, how complicated are these?
Yeah, so you can decompose this one, for example, this one into 8 controlled swap gates. The Toffoli gate. yeah. So to implement this one, you have to consume linear number of how to say Toffoli gates to the number of copies, linear scaling to the number of copies.
Okay, so I guess this turns back to the question that was asked in the previous talk, that currently these controlled swaps are difficult to implement. So if you need multiple rounds of this, then the error should add up. Okay, so what I mean is, what is the regime that we might, this scheme might be practical right now?
Yes. So if you write this form into the circuit picture, you will see you see many controlled swap gates. But actually, we can do the same in the photonic scenario. Then you don't have to even introduce the additional ancillaries or the controlled swap gate. So we hope our gadget will be especially useful in this platform.
Just a follow-up question. So have you done any analysis so in this scheme, we are assuming that the ancillas are noiseless, right?
Well, yeah, that's true. I mean, this part, all of these parts are
So do you have any estimates of what might happen if there's noise in these parts as well?
Yeah, actually, this is a nice question, which also applies to GenU's framework. But yeah, we have. No, they analyze the noisy case, but we are doing the analysis.
So essentially, it depends on your circuit noise, right? So what this noise will do is essentially, okay, you mitigate all of the circuit noise, but you add this tiny bit on top. So as long as the noise bring by this additional bit is much smaller compared to the circuit noise you are removing, then you'll be good. And you can see that this is a linear number of gates. Even if it's Toffoli or things like that, this is just a linear number of gates compared to usually a circuit you will want to run like linear depth, which means n square gates or like even much more. And then for the ancilla and things like that, you can even implement additional error mitigation on top of it, because it's just one single qubit or two like log number of qubit, which is very easy to characterize their noises.
Yeah, that's right. So this also has the balance point, in the sense that you increase the depth of the circuit, you won't be, how to say, you won't harvest any how to say advantage over this. Thank you, Eugene.
Let's thank both speakers of the session again. And head to the coffee break. Oh. Did I do that? Yeah, it's off. Yeah, well, where are you? What's that room are you in?
Next one here.
Here? Yeah, so it'll be different just that you can clip on your belt, just that you can put on your phone. Yeah, yeah.
Try to speak. Yeah, okay, it's on. Okay, let's maybe turn. Okay. Since it's 3, I propose that we start with the talks of the last session for today. First person speaking is going to be Libor Zaha, who's going to talk about a colossal advantage. The stage is yours.
Thank you very much. So, yeah, I turn it on. Okay, so I would like to tell you about our quantum advantage result, and this is a joint work with Xavier Quattrochois and Robert Koenig. Is it better or? Can you hear me now? Is it better or? Is it better now? Can you hear me? Yeah. Okay. Okay, can you hear me now? Good. Okay, so today I would like to tell you about our quantum advantage result, and this is a joint work with Xavier Quattrochois and Robert Koenig. And so our work is not about quantum advantage against efficient classical computation, where we can only get results which are based on some complexity theory assumptions, but we will restrict ourselves to some restricted models of computations, those of shallow depth classical circuits and shallow depth quantum circuits. And there we can actually prove some unconditional results. But how do we want to target this? We want to go somehow close to what is physically realizable. So we will consider noisy circuits with some local geometry, for example, 3D local geometry. And what we would like to have is we want to have some strongest quantum advantage that we can get. So we will consider also some unbounded input gates for the classical circuits. Okay, so let me briefly tell you about some types of shallow depth circuits. So the most basic one is something which is called NC0, and this is class of circuits, which it's a classical, those are classical circuits which has bounded Fenning gates, and they have constant depth. The depth means that it is the longest path between any input to any output, and the Fun-in is the number of inputs to a gate. But we will be more interested in AC0, which is actually the type of circuits to which we are targeting our quantum advantage. And those circuits can also contain some unbounded Fun-in gates, like unbounded AND and unbounded OR. And we will also be talking about the size of this circuit, for which we need polynomial size. And the size is number of gates. So what is the relation between those circuits? So by a simple Lightcon argument, where you just simply trace out what kind of inputs influence the output, you can see that you cannot compute AND on all of the input bits by this type of circuits. But you can do it in the AC0 circuits. Okay, and you can also show that there are things which you cannot compute with the AC0 circuits. So for example, you cannot compute parity, and this can be done by something which is called restriction-based methods, about which I will tell you a little bit later. And so you might kind of think like how far we can get with this. So let's say that we add there the parity, and we consider circuits which also can compute parity. And you might be wondering how far we can get with these unconditional separations. And actually not that much far above this AC0 with parity, this AC02. Actually, if you consider mod gates, which computes modulo of product of two distinct prime numbers, then we don't even know whether they don't contain NP complexity class. Okay, so how to show circuit lower bounds for AC0 circuits? This will be done by, or one of the methods is random restrictions, where we choose some inputs randomly and we fix them to random values. And for what I would like to give you a little bit of intuition is that if we do this, then these random restrictions will severely simplify AC0 circuits, and the functions which survives these random restrictions, such as parity, they will be hard for AC0 circuits. Okay, so how to somehow get an intuition behind this is by viewing these AC0 circuits in their normal form. And actually, this is where this name AC comes from. It's the A stands for alternating and C for circuits. So those are circuits which has alternating layers of ANDs and OR gates. And the main technical thing there will be something which is called switching lemmas, where what we would like to do is we would like to switch the consecutive layers of AND and ORs and see what happens. And so if you do it without these restrictions, this can blow up your circuit exponentially. But if you apply restrictions here, then what happens is that it actually simplifies your circuit in a way that it will not blow up. Okay, so what you can do is that you can apply this inductively and you can shave off your circuit up to just 2 layers. So by these random restrictions, you will end up with a small depth to AC0 circuit. And the typical proof with this kind of switching lemmas will be, so let's say that we want to prove that you cannot compute parity by AC0 circuit. So you show that by these random restrictions, you will need to have a small depth to circuit. But if you consider a circuit that should have computed parity, then on the remaining 3 inputs, it has to compute either parity or the negation of parity. And then you show that you need to have a very large, exponentially large circuit to compute parity if you have just depth 2. And this will give you the result that you cannot compute parity in AC0. But we will be using some kind of newer types of switching lemmas, which are stronger and possibly with some additional restrictions, where you take the random restrictions and it tells you that you have to restrict some additional inputs to random variables. And the result of this thing, at least in some operational meaning, will be that if this was AC0 circuit, then this restricted circuit could be implemented by these NC0 circuits with high probability. And I recall that this NC0 circuit, this was the bounded Fanin constant depth circuit. And the number of inputs, which are still free, will be somehow sufficiently large. Okay, but let me get back to the quantum circuits. So there is an analog of this NC0 complexity class, which is called QNC0, and those are just constant depth quantum circuits, which could possibly use some ancillas. So where those fit? So if you consider only decision problems, then you will not have any quantum advantage with those, because you can again trace out some kind of Lightcon argument, and because everything has constant degree, then you can just simulate it by NC0 circuit. So there is no quantum advantage there. But if you consider relation or search problems, where you have multiple output bits, then you can actually get some quantum advantage. And there is actually right now quite a bunch of results regarding this. So we know that those circuits cannot be simulated by NC0 circuit or AC0 circuits. And there is even a result, which is under complexity theory assumption by Terhal and Di Vincenzo, that unless polynomial hierarchy collapses, then you cannot even efficiently simulate them. And this is where our result will fit in. So we will consider 3D local circuits because we are trying to target something which is close to something being physically realizable. Okay, so first we need to consider a noiseless case for which we prove that 1D local QNC0 circuits are not in AC0. And so we will be dealing with gate teleportation circuits, and the main building block of this is gate teleportation, where we take some unknown quantum state and we teleport it through a Bell state on which we a priori applied some unitary gate. And now if you do this, then what you end up with is this unknown quantum state, which is corrupted by a Pauli error, which is determined by the result of the Bell measurement. And you have this unitary U applied to it. Okay, and in the typical scenarios, what you do, you apply a correction and get back to the state that you would like. But what we will consider, we will not do these corrections actually. So here, if you, let's say that I have n qubit state and those unitaries, they are 2 qubit unitaries, and I applied this kind of sequence of gate teleportations on them. And so what this thing effectively does is that it will implement you this sequential application of the unitaries with these random Pauli errors in between, which are determined by the results of the Bell measurements. But the nice thing about this is that you don't have to wait for this state to be prepared, and you also don't have to wait for the measurements. So what you gain here is that you have this kind of parallelization for the price of these random Pauli errors. And this is actually something that was used in the result by Terhal and DiVincenzo, which was way ahead of its time. So this is by some kind of post-selection argument, you can use this to show that you cannot simulate QNC0 circuits efficiently under some complexity theory assumptions. So what we will consider single qubit Clifford gate teleportation circuits, and we will show that with those you will get advantage against AC0. Okay, so we have this kind of circuit. So this is like a cyclic application of those gate teleportation circuits where the inputs are these Cliffords, which are classically controlling these gates, and the outputs will be the Paulis, which are the results of the Bell measurements. So this circuit is trivially in QNC0, and we will consider for our problem definition something which is called possibilistic simulation, and this is like the simplest notion of simulation you can come up with, and the task is to just output any Paulis P0 to Pn-1, which can appear with non-zero probability in the output distribution. Okay, and we will show average case result that any AC0 circuit which would solve this problem for uniformly random chosen input of these Cliffords with this kind of constant probability will need to have size at least this sub-exponential. So there is a particularly nice formulation of this problem, which is that you have to satisfy this equation with the trace. And this thing will directly imply the result that I advertised. Okay, so how do we prove these lower bounds? We will do it by contradiction. So we will assume that you can do it, and we will get a contradiction with the fact that you cannot, that a classical strategy for a Mermin-Perez magic square game cannot have probability of winning more than 8/9. So first we will use the random restrictions. So for this, we needed some kind of strong version of the random restrictions, for which we additionally need to consider block fixing because we represent Cliffords by 5 bits. And so if we do this, then we basically end up with high probability with something which can be implemented with NC0 circuits. And for those, we already can apply some kind of Lightcon argument. So we end up with this kind of circuits which has unbalanced number of inputs and outputs. But by some probabilistic argument, you can show that there are 2 of these inputs which has non-intersecting light cones. Okay, and so what we will do right now is that we will try to somehow change this problem into this formulation on which we can apply this non-local game type of arguments. And the way how we do it is that if you imagine that you rewrite this problem in this algebraic formulation where I marked the dependence on both of these light cones, there then we can use commutation relation between Clifford's and Pauli's to and grouping of both of them to transform it into the circuit that we wanted. And now I don't want you to follow this, but we can do this grouping and commuting in a way that we don't pick up some additional dependency. So what we have right now, we end up with this kind of circuit where those are both F and the G's and U and V's are somehow grouped, and it might be not so easy to calculate them, and you might not be able to calculate them in constant depth, but we preserve this light cone structure. And so what we will do now, we will play some magic square game with this circuit. And the game that we will play on this circuit is Mermin-Perez magic square game, which is a cooperative game of Alice and Bob. And there is a referee which sends them two numbers, alpha and beta, which are from 1 to 3, and they are asked to output each 3 bits in a way that for Alice, they should be of odd parity, and for Bob, they should be of even parity. And additionally to that, they should satisfy this matching condition. So for X alpha and Y beta, they should be the same. And by a simple parity argument, you can see that a classical strategy, but even with some shared randomness, cannot be win with probability more than 8/9. But if you consider quantum players, quantum Alice and quantum Bob, which additionally shares 2 Bell states, then they can win this game with certainty. Okay, so we have this kind of type of circuit where we have these big measurements that are measuring these observables with which you can win this Perez-Mermin magic square game. So how do we use it in our scenarios? So this formulation of the game, it's not the only one, and you can have more of these magic square game measurements. There is one which is particularly nice, which you can actually play by using this single qubit Clifford Gates and Bell measurement with some additional post-processing. So if we would be able to have this simulator in AC0 for our single qubit Clifford Gate teleportation problem, then what we get is that there would be a classical strategy for Mermin-Perez magic square game, which will win with probability more than 8/9. Okay, so this is for the noiseless case, and our main result is actually about the noisy case, which is by a simple application by a non-standard fault-tolerant scheme of Bravi, Gosset, Kenicht, and Thomas-Michel. And this is only possible because the problem has this kind of nice and very simple structure. So the type of noise that we consider for our circuits is something which is called local stochastic noise. And this is a random Pauli noise where the errors can possibly be correlated, but the probability of the Pauli errors is dropping exponentially with the size of the support of the error. And so if you would try to apply some standard fault-tolerant scheme on your constant depth circuit, everything will blow up, and so you will not end up with constant depth circuit, which you actually want to show the quantum advantage. But what Bravi, Gosset, Koenig, and Thomas-Michel considered is that they looked into the associated relation problems with the ideal circuit and for the fault-tolerant circuit, and they've been able to fold some parts of this fault-tolerant computation into the definition of the relation problem. So if the circuit satisfies some certain properties, you can do this thing. And actually, our single qubit gate teleportation circuits do satisfy this, so we can use this construction to transform our 1D local ideal circuits into 3D fault-tolerant circuits for a modified relation problem, for which we still can show that you can have advantage against AC0. And this construction leads to this iconic shape of the underlying layout of your circuit, which maybe reminds you of something. It certainly does to us. And this is where the title of our paper comes from. Okay, so this is our theorem. And so we showed that a noisy 3D local QNC0 is not contained in AC0. And I will end here and take any questions you might have. Thank you very much.
Okay, are there any questions?
Oh, hello. Thank you for a very nice talk. And sorry, I have a very fundamental question. Can you explain again what is AC0?
Yes, so AC0 is constant depth classical circuit, which you are allowed to have unbounded Fan-in AND gates. So you can compute AND and OR on as many inputs as you want. So you have these two gates and you have also NOT gate. And your circuit should have constant depth, which means that if you view your circuit as a directed graph, the path from the input, from like the longest path from any input to the output should be constant, and the size of your circuit should have polynomial size.
Okay, thank you. I have another question, which so basically, as shown in your work and other works, we know that if you restrict the depth of the quantum circuit to be some constant, then we have some separations between quantum and classical. My question is that can we restrict the number of qubits? For example, if I don't restrict the depth of the circuit, but I only consider a constant number of qubits or the constant number of bits, classical bits, can you find some? Do you think there is some separations?
Yeah, I'm not so familiar with this, but if you have just constantly many quantum bits and you are not scaling it, and then okay, I don't want to guess.
Oh, okay, thank you.
I use the chance to ask one myself in the meantime. So you were mentioning that you were looking at possibilistic simulation, if that's correct. How come you chose that over other ways of simulations? That seems a very weak form of simulation, since you just need to find one output with non-zero probability. Is that correct?
So it is like that you define the problem so that your classical computer has you make it easier for your classical computer. So it is a weaker notion of simulation that, for example, I don't know, sampling from the output distribution or strong simulation, other things. So yeah, I mean, the same holds also for the stronger types of simulation, but we wanted to make the problem like the easiest for the classical device.
Any other questions? There's a question in the back.
Thank you. Just a simple question. Can you explain again why is it called colossal?
Okay, so the layout of your fault tolerance implementation looks like this. and it reminds us of a Colosseum. But like traditionally, people would call this kind of separation exponential because, I mean, it's more sub-exponential because you show this sub-exponential lower bound on the circuit size, but we choose to use colossal.
Okay. Still not really intuitive, but yeah, thanks a lot.
Okay.
Okay, maybe we can take further questions later. Let's thank the speaker again.
Try. Hello. Okay. Sure. And to change?
So you've got this one here.
Okay.
There you've got the laser pointer, and this should be going up and down. Working?
Yes. Yes.
So I'll try to.
Yeah. 15. Perfect. Yeah. And also possibly 1 minute before, say,
And
one.
one.
Yeah. So I can decide
If
if.
you look at mid-point.
Yes. We can decide how much to spend on the conclusion or not.
If you take 1-2 minutes more.
Okay. No, I mean, I tried. There should be.
Okay. Yeah.
Yes. Yes.
Okay, let's start with the next talk of this session, which is by Antonio, who's going to be talking about noise-induced shallow circuits and absence of parent plateaus.
Okay. Hello, everyone. My name is Antonio, and today I'm going to talk about noise-induced shallow circuits and absence of barren plateau. And this is a joint work with these great people, Armando Grisani, Shomik Ghosh, Sumit Khatri, Jens Eisert, Daniel Silfranca, and Yihui Kwek. And after the talk, if you want to have an additional chat, feel free to reach both me and also Daniel, who is here in the audience. And it was a really crucial contributor to this work that I'm going to present. Okay, let's start with a spoiler of what we will see. We will show that if we have a circuit architecture where this is represent the noise in a quantum circuit, for most of the realization of this circuit, only the last few layers will matter to estimate observable expectation values. And this will imply efficient classical simulation and lack of barren plateau for realistic noise model. And we will see in precise terms what this means. Okay. The outline of my talk is to start with the introduction of noise in quantum circuits, then move to this effective shallowness of noisy quantum circuits, and then classical simulation of Pauli expectation values on noisy random circuits, and then move to the barren plateau. Okay. Understanding noise, the impact of noise in current quantum device is crucial for harnessing the capabilities and the limitation of this noisy device. And many previous works model the noise as solely depolarizing. And this is the definition. A depolarizing noise and a state in a convex combination between the state itself and the maximum state. And it has been shown that depolarizing noise induces catastrophic phenomena in quantum computing. For example, in the near term, depolarizing noise induces barren plateau in variational quantum algorithms, and also renders random circuit sampling supremacy experiments efficiently classically simulable. However, it has been pointed out that tiny departure from this model could lead to different conclusions. For example, in the context of fault tolerance, error correction, and also in the context of random circuit sampling, where it was shown that both easiness and hardness arguments for circuit sampling do not hold anymore if the noise is different from depolarizing. Okay, and the depolarizing noise assumption, if true, enormously constrains noisy computation. For example, let's say that we have a circuit like this, where the noise acts after each layer, each two gates, and we have the depth L that is larger, and we have the depolarizing noise, and the depth is larger than log n. It can be proven that we have an exponential convergence in trace distance of 1 norm to the maximum state for any realization of these circuits. And this L is the depth of the circuit. And this was shown in this work by Müller-Hermes, Daniel Silfranca, and Michael Wolf. And also before that, it was pointed out that through this convergence of maximum state, only the quantum computation with depolarizing noisy circuits is possible until log n depth. And for example, for the task of estimating Pauli expectation value, this implies that simulating Pauli expectation value of deep depolarizing noisy circuit is trivial, because from this, it follows that this inequality, that for deep circuits, for R large enough, outputting 0 it gives a very accurate approximation of your Pauli expectation value. And more generally, for deep efficient classical simulation of all deep depolarizing noisy circuit is trivial, because in general also sampling is trivial because you can just sample from the maximum state, from the uniform distribution. And however, this kind of inequality strongly relies on the assumption that the noise is depolarizing. And for noise different from depolarizing, not all circuits become trivial after log depth. After log depth, this quantity here is more than inverse polynomially small. And if we have, for example, amplitude damping, this is not true anymore. And the real hardware noise is not solely depolarizing, which is a particular type of unital noise, where this is the definition of unital noise, that the noise fixes the identity matrix. And the other noise components, for example, T1 error, amplitude damping, are non-unital, which means that this equation is not true. And strikingly, in this paper, Quantum Refrigerator, it was shown that if the noise is non-unital, one can choose carefully the gates in the circuits to make these circuits fault tolerant without using fresh ancillary qubit during the computation. Like, okay, and so if the noise is non-unital, one can carefully engineer the circuit to perform reliable quantum computation also after log depth, while quantum computation with depolarizing noise is possible only until log depth. This is not true for non-unital noise, as is shown in this paper. So if DPP different from BQP, Pauli expectation value of worst case non-unital noisy circuits cannot be efficiently estimated classically. So a question naturally arises, that is, what happens for generic noisy circuits? If I take an instance of these circuits where these two qubit gates I sample uniformly at random, and I ask you, with high probability over the choice of the circuit, estimate this particular Pauli expectation value. Can we solve this task efficiently? Okay, our work address this question, try to answer this question, and we'll see. Okay, what happens for generic noisy circuits where this noise we consider general kind of noise, NECP-TP map single qubit? Okay, we show that only the last log n layers matter to estimate expectation value up to inverse polynomial accuracy for most circuits. And the intuition behind this result is that if nothing is clever is done to choose the gate to take advantage of the noise, the content of this part of the circuits is forgotten. And this is in contrast to the polarizing noise, where for deep circuits, no layers matter because you reach the maximum state. Even if you change the gates, this will not affect the result. And this is also for all circuits. And we show that if the noise is non-unital, instead, the last log n layer do matter, but for most circuits. And yeah, and this will not matter for most circuits. And in more technical terms, we show this proposition that for any initial state rho 0, possibly complex and observable O, this inequality holds, where this expected value should be read like with high probability this inequality holds over the choice of the circuit. And this is the target expectation value, where phi is the noisy circuit. And here, phi, this quantity here represents the circuit truncated where only the last k layers are considered. And sigma 0 is any preferred initial state. You can put your favorite state like the 0 state. And the error approximation decays exponentially with the depth of your considered last layer. Okay, and so if you want this error to be inverse polynomial small, k equal log n suffice to have any inverse polynomial accuracy. Okay, and this follows from the more general theorem that is we show that for any k depth circuit phi k states rho and sigma Pauli p, we have this inequality where the error decays exponentially both in the Pauli weight and this depth k. And this from standard norm inequalities implies a trace distance convergence, that if we have the depth of the circuits larger than n, omega n, and for any states rho and sigma, over which we apply the same noisy random circuits, we have an exponential decay of this trace distance. And this omega n probably is loose and might be improved probably with the more sophisticated techniques, probably to log n. And one can wonder if a result like this might be shown without this expected value, but one can cook up easily some counterexample. For example, choosing dephasing noise and classical circuits like topology gate and some classical input state, one can see that this inequality without expected value is not true, cannot be shown in general for any noise. We saw that it's true for the Parisian noise, but for any noise, this inequality cannot be shown without expected value. And in particular, more interestingly, this paper, as I said before, quantum refrigerator showed how to average non-unital noise to perform fault-tolerant quantum computation without fresh auxiliary qubits. And however, in certain eigennoise regime, we can obtain this inequality that for depth larger than log n, and of these under some certain parameters of the noise map, single qubit noise map, we have this inequality without expected value. Okay, and okay, so what we've discussed so far give us a classical simulation algorithm for simulating noisy random circuits with general noise. And so the task is estimating this Pauli expectation value with type probability over the choice of phi with some accuracy, with some wanted accuracy. And we have seen before that if we take just the last k layers of the circuit, with type probability over the choice of the circuit, we have the error of approximation that is exponential in these last k layers considered. So if we want this quantity here less than epsilon, it suffices to choose k equal log epsilon minus 1. And so the time complexity of this is just outputting this quantity. And this can be done by working the Heisenberg picture and through standard Letcon arguments. If P is a local Pauli, and phi is these layers of quantum circuit, then this is also this observable is local. So okay, a Letcon argument can be taught, for example, with this kind of schemes. And yeah, so if we have a k-depth circuit of local Pauli, the number of effective qubits in the Letcon is order k. And the cost of a quantum computation of k qubit is exponential in k. In at least this figure is 1D. So the computational time for 1D is exponential in order k, and k is log epsilon minus 1, so we have a Pauli epsilon minus 1 to simulate this Pauli expectation value with type probability over the choice of the circuit. And in general, we have this theorem that holds for any dimension, that given a randomly sampled noisy quantum circuit for any depth and noise, there is a classical algorithm to estimate local Pauli expectation value to epsilon at the precision with type probability over the choice of the circuit. And the runtime is this exponential in the number of effective qubits in the Letcon. That depends by dimension, constant spatial dimensionality of your circuit. And this is for general D dimension. And this for D equal 1 is Pauli epsilon minus 1, but for D larger than 1 is quasi-Pauli in epsilon. And we don't have any dependence by the number of qubits and depth. So for constant epsilon precision, the algorithm is efficient for any dimensionality. And for epsilon inverse polynomially, the algorithm is efficient only for 1D with this algorithm, and quasi-Pauli for a larger dimension. And for constant precision, the algorithm is efficient also in possibly all-to-all connectivity, by the way. Okay. And one can ask about global Pauli expectation value. For this task, this case, the problem is trivial because we can show that Pauli expectation value are suppressed with the Pauli weight. So for simulating Pauli expectation value of global Pauli, it suffices to output 0 and succeed with high probability. And we also give a condition to verify the success of the classical simulation. That is basically check if the Heisenberg evolved observable is close enough to the identity, to something proportional to the identity. If it's true, then you know that you picked a circuit where this classical simulation works. Okay, let's move to Barre and Plateau. And barren plateau is a phenomena that was born in the context of variational quantum algorithms, and where the problem is encoded into find the minimum cost function that depends by some parameter that are the parameters of the gates. And the definition of barren plateau is informally, if for most choices of this U1, UM, cost landscape is essentially flat. And also the gradient norm is very small. And cost functions are usually made by Pauli expectation values. And one can ask, do variation in the gate mu influence C? This is captured from the partial derivative. If the partial derivative is 0, this means that the cost function does not depend by this parameter. And yes, and if the partial variance of the partial derivative is exponentially small by Chebyshev inequality, this implies that the influence is very unlikely. And in quantum machine learning jargon, this means also that the gate is not trainable. And previous works have shown that in the noiseless case, at depth larger than omega n, we have exponential concentration of cost function, and the partial derivative exponentially small. And this is essentially, the intuition behind this is that the circuit, where we assume that these gates are random, converge to approximate to the sign. And these are second moment quantities. And in the depolarizing noise regime, it was shown the same of this noiseless case, and this is the intuition behind this is the fast convergence to the maximic state discussed at the beginning. And for non-unital work, non-unital noise, our work kicks in, and we show that we don't have barren plateau at the depth for local cost function. In particular, the variance of the cost function is omega 1, and the variance of the partial derivative decays exponentially with from the last layer. And so we show that all the last log n layers are trainable, the gates here. And please compare our work with this other nice work that came out a bit before us by Singh Kanipa and Daniel Idar, where it was analyzed barren plateau phenomena beyond unital noise. And okay, in more technical terms, here we find the formula for the variance of the cost function with respect to here it's Janic observable, and we show that it's each Pauli component is suppressed with the Pauli weight. And this implies that local cost function, like Z1 expectation value, do not suffer from exponential concentration, and the global cost functions suffer from exponential concentration, like Z tensor n. And for the partial derivative, we show that for any noise, we show this upper bound for the partial derivative that is suppressed both with the depth from the end and also with Pauli weight. And we show for local cost function a matching lower bound, which shows that these last layers are actually trainable. And these are corollary of this is that the gradient norm is omega 1 in average. So we show absence of barren plateau. And if P is global, then for any gate, we have still that any gate is not trainable. And for the particular case of unital noise, our results imply is that in each gate, each partial derivative with respect to any gate in the circuit is suppressed exponentially in the depth of the circuit. And this generalizes previous works because assume general unital noise without any additional assumption like works, for example, for dephasing noise. And okay, proof ingredients are working the Heisenberg picture to design properties and using a normal form of noise channels, which is useful when you have some kind of unitary invariance, you have some kind of sparsity in the Pauli transfer matrix. And our numerical experiments confirms our result for more structured circuits. One can wonder if the true design assumption of the 2-qubit gates is necessary. Our numerical example says probably not. And okay. And conclusion is that any amount of non-unital noise induces lack of barren plateau, but it truncates most circuits to effectively logarithmic depth, allowing efficient classical simulation in estimating Pauli expectation values. And also, we have seen that depolarizing noisy circuits are restricted to log depth. But also we mentioned that if one carefully engineered the circuits to take advantage of non-unital noise, one can perform quantum computation more than log depth. However, our work says that most circuits behave like log depth circuits, effectively log depth circuits. So we can say that unless we carefully engineer the circuits to take advantage of the noise, it's unlikely that the non-unital noisy circuits are preferable over depolarizing noisy circuits. And assuming oversimplicity model could be misleading because we will show that the absence of barren plateau with non-unital noise, but this absence of barren plateau is not a useful absence of barren plateau because of the effective shallowness. And the open question is simulating Pauli expectation value on noisy random circuits with inverse polynomial accuracy in 2D and all connectivity in polynomial time. Our algorithm is efficient in 1D. And we have some work in progress where we improve a bit this, but yeah, it's mostly open in all-to-all connectivity for general noise model. And the complexity of classical simulation of random circuit sampling with non-unital noise is still open, as pointed out in this work, Fermendol, effect of non-unital noise or random circuit sampling. And the depolarizing case was addressed in this Aranov et al. Talk at QAP. And yeah, with this I conclude. Thank you a lot for your attention.
Thank you very much. Are there any questions?
Yes, thanks for the talk. My question was, you were saying that if you have depolarizing noise and your circuit is too long, then you have just pure noise at the end, and yeah, it's a useless circuit. And that if you have non-unital noise, then you have the last log depth that can be used to do some computation. Can you have that if your circuit is too short, then your non-unital noise is basically equivalent to depolarizing noise, and that you need to make your circuit longer to be able to make use of the last log n?
Okay, it was shown that basically depolarizing noise circuits are useless if you have a circuit larger than log n. So you are restricted to quantum circuits that are less than log n if you want to do something useful. We also show that if you have a circuit larger than log n with any noise, only the last log n layers matter on average. While it was also known that if for worst case circuits, this is not true. So I mean, one way of reading this result is that I mean, unless we carefully engineer the circuits to take advantage of the noise, it's unlikely that non-unital noisy circuits are preferable over depolarizing noisy circuits, which are restricted to log depth. Yeah, I mean, if you don't do anything clever, probably you are restricted to log depth both ways.
Okay, thanks.
Yeah, so there was a paper from 2020, I think, where there was shown that any noisy quantum circuit can be effectively simulated with tensor networks, where I think the noise model they used was just like, if the gates are low fidelity, then you can like do it as accurately with tensor networks. How does that relate to this work? Is that kind of noise, does that belong to any of your noise models here?
Okay, I'm honestly I don't know the paper that you are talking about, but okay, as far as I know, I mean, those works analyze some kind of, there were previous work that analyze Pauli noise or different kind of noise. Here we are, we don't have any assumption, for example, on this effective shallowness, we don't have any assumption on the noise apart from being non-unitary, that is not a unitary map, and that is local. As far as I know, previous work assumed assumption on the noise.
Any other questions? There's one in the back.
Thanks for the nice talk. I wanted to ask, so if I'm not mistaken, the paper that you mentioned on quantum refrigerator, it somehow exploits the knowledge of the fixed point of the non-unital noise. In your analysis, do you use the knowledge of the noise map at any point, or you only rely on the fact that it's non-unital?
Okay, 1 second. Okay, this theorem here holds for any noise that is non-unitary, that is not a unitary channel, and holds for any noise that has parameters that are constant in the number of qubits, like which we expect if we take the model of noise that is local. And yeah, so for this theorem, you don't, holds for any noise. However, for the classical simulation, yeah, you need to know the noise. I mean, we assume that we have a quantum circuit written on our computer or our piece of paper, where we know the details of the noise parameter. Yeah, we want to classically simulate this circuit that we have.
Okay, thank you.
Okay, let's thank Antonio again.
Oh, I have like. Does that work? Oh, is it on? Oh. Hello. I see. I see. Oh, I have it here. Hello? Oh, okay, that is weird. I can talk loud? No.
You can give it a try. If it's not loud enough.
I see. Is it being recorded or like well? Okay, and this works or? Okay. Okay, wait, actually maybe I'll just use this so I don't feel like I'm playing with it.
Whichever's more.
Oh.
Okay, we'll start with the last talk for this session. Natalie's going to be talking about identity check problem for shallow quantum circuits.
Thank you. So hi, everyone. Yeah, I'm going to be talking about this joint work on the identity check problem with joint work with Sergey Bravi and Min Tran, who are at IBM. Okay, so we're kind of just going to talk about a pretty simple problem. That problem is I give you two different quantum circuits, and I ask you, are they the same circuit or are they different? You know, maybe the gates aren't the same, but I just want to know, are they implementing the same unitary? You know, I could also ask you, I give you one circuit and I ask if it is the identity or not. And, you know, as you might guess, or you might be able to tell, these are the equivalent questions because, you know, you can just do U v dagger. And it's a very simple question, but there's many applications. So one is invalidating quantum algorithms. So, you know, here's the quantum Fourier transform circuit from Nielsen and Chuang. But, you know, for whatever reason, maybe in your quantum computer that you keep at home, you know, you can't implement all these gates, so you have to implement it this way. But, you know, ideally, you'd like some way to verify that it's the right circuit, or let's say someone just gives you the circuit, like a student in your quantum information class, and you want to grade their homework. How can you tell? So another application is for developing quantum algorithms. So, you know, maybe you have some parameterized quantum circuit, and you want to tune your parameters so that you can implement some unitary V as best you can. And so if you have a way to tell how close these are, then, you know, you can try to do some sort of optimization algorithm over your angles. And, you know, one example of this is when you're trying to minimize Trotter error in Hamiltonian simulation. And also, this is like a pretty interesting question from a complexity theoretic standpoint, because as I'll talk about soon, estimating the distance between two circuits turns out to be QMA hard. Or I mean, you know, more specifically, you have this non-identity check and the identity check, which are QMA and co-QMA complete. And so, okay, I mentioned that this actually turns out to be really hard to estimate. So in particular, right now I'm talking about to within, you're trying to estimate this distance to within additive inverse polynomial error. And so in the general case, when you have some quantum circuit and you're allowed measurement and maybe you're allowed to trace stuff out, this problem turns out to be p-space hard. Oopsie. But you know, if we restrict ourselves to just unitary circuits, then this problem is still QMA hard. And I don't know if you guys, I don't know if this is surprising or not, because, you know, we're trying to tell something about, you know, these polynomial sized circuits. Maybe it makes sense that you would need a polynomial sized circuit to know. But, you know, you could ask this question about, you know, really simple quantum circuits. So like, for example, these constant depth quantum circuits that are like geometrically local in one dimension, meaning like your qubits are laid out on a line and you're only allowed nearest neighbor gates. Like these circuits are really easy to simulate. You know, we can calculate output probabilities, we can sample from them. But actually still the identity check, like calculating how close the circuit is to identity, is still QMA hard, which is, you know, maybe surprising. And so, okay, you know, I've been talking about distance, but I haven't really defined anything. And so the hardness results I talked about on the last slide, you know, actually hold for a variety of distance metrics you might be familiar with. But the two that we're going to focus on in this talk are spectral norm and diamond norm. So, you know, spectral norm is just the maximum eigenvalue. Diamond norm is defined for channels, and it's a bit weirder, but the physical interpretation is that, you know, if you have some experiment that uses your unitary U as a subroutine, and then you replace it with the identity, this diamond distance is tells us, like, bounds the total difference in the like outcomes of your experiment in total variation distance, whether or not you use U or identity. And there's also a geometric interpretation of these two different norms. So, you know, a unitary U has all of its eigenvalues on the unit circle, and the diamond distance is actually, like, if you look at the convex hole, of all the eigenvalues, it's going to be this like diameter of a polygon. And the spectral norm distance is going to be like you look at the furthest point from 1, and it's the length of that thing. And in this talk, we're going to be focused on diamond norm, which we call delta of U. But in our paper, we also have a result for this other spectral norm. Okay, so now I'm going to talk about like 2 different ways you might try to talk about error when you're trying to have like an approximation algorithm. So the first is additive error, which is what we've talked about so far. So if you have additive error epsilon, this means your estimate is between, actually like delta minus epsilon and delta plus epsilon. On the other hand, you might have multiplicative error, where your estimate is like an upper bound on the true delta, but it's also a lower bound with this factor of alpha, which is going to be greater than 1. And as I showed, getting this additive error to be like on the order of 1 over polynomial is QMA hard. And so this tells us that, okay, for multiplicative error, it's also hard if you have additive, or if your error factor is like 1 plus 1 over polynomial. But you could ask, what about if your multiplicative error is bigger? Like, what if it's constant, for example? Is it feasible then? And in this paper, we show an algorithm for estimating this diamond distance up to like constant multiplicative error. In particular, if your unitary has depth h and or if it's implemented by a circuit that's depth h and geometrically local in d dimensions, then we get an estimate that has approximation ratio alpha. And yeah, the runtime is like this ugly thing. But when you plug in constant depth, constant dimension, this is linear time. And so, even though this problem is QMA hard for like inverse polynomial additive error, turns out that, we actually can still get an approximation algorithm if we, tweak what kind of approximation we care about. And, one thing I'll note is that in the case where delta is like really small, like inverse exponential, then this estimate is like extremely good. Like, much better than like a 1 over poly additive error. And so now I'll give a high level overview of how the algorithm works. And to just help us, we'll kind of keep this 2D, like this 2-dimension quantum circuit picture in mind. So first, we're going to color all of our qubits so that each color kind of has many small clusters that are like spatially separated. So here you can see there's like all these red regions. And you can think of the red regions as being like constant size. And each of the red regions are like pretty far from each other. And okay, now we're going to consider the channel that applies our unitary U and then traces out or throws away all qubits that aren't blue. And so we can look at these blue regions that I labeled like B1 through B8 in this case. And then what we're going to do is we're going to estimate how far this channel is that just outputs only the blue qubits, how far it is from, if we did the same thing to the identity channel. And the way we're going to make this estimate is going to exploit the fact that this blue channel has a product structure if we like have these blue regions sufficiently spread apart. And finally, our estimate is just going to be the sum of all of these estimators for each color. Okay, so now I'm going to get a bit more into how we make these estimates. But first, it's nice to kind of have the following nice observation. And hopefully people here are a little bit comfortable with tensor network diagrams, but it won't be too crazy. So a really nice fact that we're going to exploit is that if your diamond distance isn't root 2, which is like the maximum your diamond distance can be, then you have the following thing where, this first object is like, okay, so now if your unitary acts on n qubits, now we have like 2 n qubits. So like this orange wire is like an extra qubits. And first we swap these 2 registers. We apply U dagger to the first register. We swap back, and then we apply U. And overall, we're looking at the spectral norm of this object minus just identity on both qubits. Okay, why is this the case? This is kind of strange, maybe, if you haven't seen this. So it follows from 2 pretty nice facts. The first is that, this delta of U equals, the norm of the U tensor U dagger minus identity. And the second is that, if you follow me so far, then okay, we have U tensor U dagger. Now we can just move this U dagger under, and you're allowed to do this. And what this corresponds to is just you swap, you apply 1, you swap back. You could have just like applied them separately. And so, okay, so now what we want to estimate, right, is this weird swap, this like weird swap object minus identity. And here I've recolored. Okay, the drawing has lowered in quality, but also it has colors now. So the I colored. Yeah. Okay. So according to the coloring, I've like just now have wires so that there's a new wire for the red wire resembles all the red qubits and so on. Yeah. And okay, so we want this thing, but instead, like I don't know how to compute that. So instead, what I can tell you how to compute are the following 3 things. Where, okay, we don't swap everything, but first we just look at this object where only the red register is swapped. Same with blue and green. And these are actually what we're going to have our estimators be for each of the colors. And okay, so we add them up. And it's kind of nice actually, just using triangle inequality. This whole thing is upper bounds the actual diamond distance on top. And also it's not too hard to show that each of these things on their own are upper bounded by the diamond distance. And so overall now, we have a approximation, like now the sum of these things is a good estimator for delta with an approximation ratio of 3. And if you were to generalize this to more colors, the approximation ratio comes from the number of colors. Okay, so now we still need to figure out how we're going to calculate this red estimator, which looks like this. Well, it looks, okay, maybe I shouldn't have revealed. It looks like this. And then because of our clever coloring, you can actually, write it as a tensor product structure like this. And each of these are going to have constant size, which is really nice because you can just, anything like any system that's constant size, we can just like fully calculate efficiently classically because, there's exponential blow up in system size, but it's constant. So whatever, that's free. Nice. So right. Okay. So we can compute each of these things on their own explicitly. So, okay. So now, writing this estimator of like this weird swap thing minus identity, what happens is because of this tensor product structure, this is going to be the maximum where you take, okay, so you have like the eigenvalues of, you look at each the eigenvalues of like K1 and the eigenvalues of each of these. And then so the eigenvalue of this thing is going to be like the sum of if you take one from each. So yeah, so this estimator is going to be like if you maximize over like phi1 from all the eigenvalues of k1, and phi2 from the eigenvalues of k2, and so on, and then this quantity where now you have e to the I times the sum of all these eigenvalues. But although we can calculate what these sets, we can calculate these sets of like eigenvalues, now we have like way too many parameters to optimize over, because like we can think about, we're gonna have like a linear number of these things. And so that's unfortunate. But we are okay because we have this really nice additivity lemma. And the like idea behind it is that if your unitary is really close to the identity, then each of these like KIs are also going to be really close to the identity, right? Like you take, yeah, it's like, I mean, if you have some unitary that's close to identity, like if locally it's far from identity, like it's just not close to identity. And okay, so this tells us that each of these eigenvalues are really small. And this makes this maximization thing easier because we can just take the maximum of each of the eigenvalues. Because like typically the reason that this thing would get expensive, this like trying to optimize over all these parameters, is that you're trying to find the like angle that's farthest from 1 on the unit circle, and you're summing over you're taking a bunch of different ones and combinations of them, and you might wrap around the unit circle, and so you kind of need to just like try every single combination. But if they're all really small and you were trying to get as far from 1 as you can, the best thing you can do is just take the largest eigenvalue or the largest angle from each of these sets, and that's how you're going to end up farthest from 1. So more concretely, you choose this angle, which is just you take the maximum angle from each of these eigenvalue sets. And if this whole thing is less than pi over 2, then this estimate is just e to the I theta minus 1. That's the right angle. And if it's bigger, then actually your whole thing is quite far from identity. And so you can just output, okay, I'm like very far from identity, and terminate, and you're fine. Yeah, maybe this is like the main technical thing I'll really go through. So yeah, hopefully it's not too messy. Okay, and so what were our, like I kind of just said our coloring allowed us to have this like nice products structure. But what actually were our coloring requirements? So we k-colored our qubits, and so I have these like k sets for each color. And what did our coloring need to satisfy? So first is that for every pair of like subsets of this coloring, so we also kind of partition them into clusters, so that for any 2 different clusters, they have disjoint backwards light cone. And I've drawn those here. And also that each of these clusters are constant size. And if this is satisfied, then we get this. Then we know that our estimator has an approximation ratio of k, where k was their number of colors. So you could ask, in 1D, you only if you have 1D geometrically local. So this means our qubits are laid out on this line, and let's say the light cones are just the cells. Like we've kind of drawn qubits here, so you only have nearest neighbor gates and constant depth. So the light cones are only kind of going to be like within a short distance. Okay, so 1D you need 2 colors, 2D you need 3 colors. Here's one way to do it. And in general, it turns out that if you have a d-dimensional lattice, you only need d+1 colors. And this was shown recently by these people. They're called like reclusive partitions. And so this tells us that our approximation ratio, this is how our approximation ratio ends up being d+1, where d is the dimension of your circuit's locality. Okay, that's it. Now I just have future directions for anyone who's eager. So the first is better approximation constants. So, we showed like an approximation ratio that was like d plus 1, a specific number, but maybe you could hope that you could get an approximation ratio that's 1 plus epsilon for any epsilon that you want. That's constant. And you might want more complex circuits. Like, is it also still easy up to multiplicative error for complicated circuits? So deeper circuits that aren't geometrically local, all-to-all connectivity, or where you allow non-unitary gates like measurement, and you can like trace stuff out. And here's a drawing of one of those. Yeah, that's all. Thank you.
Thank you, Natalie. Are there any questions?
Hey, thank you for the talk. So what about if your additive error is slightly larger, like is 1 over polylog or even constant? So is it hard or not?
I don't think like hardness is known. I would guess I think it's definitely not known for constant, because the way in which we know it's hard is like if it's basically we have like it's QMA hard if you're like really deciding if you're like really close to identity or not really close to identity. And so constant error is like kind of yeah, like just fully easy in these cases. So
Meaning like you think a constant additive error can provide a similar efficient algorithm?
Yeah, I'm not sure. I would guess that for constant additive,
Because it should be slightly harder than constant multiplicative error, right?
I guess it depends, because like depending on the regime of your,
Sure, yeah, true.
like if I don't know, yeah, like you could have some family of unitaries that have like what you want to do, they have really small distance, and then additive is like pretty easy, but multiplicative is like really hard.
Sure.
So, but yeah, I don't know. Yeah, it's a good question. Like yeah. And then for like inverse polylog error, that's also a good question. Yeah.
Okay. Thank you.
Any other questions?
Thanks for the great talk. Just one question. So you said that the additive error is QMA hard, whereas the multiplicative error, you have an efficient algorithm. Does this kind of imply that it's easier to prove something that's closer to identity than not? Because as you said, like this accuracy gets better as long like multiplicative error becomes more relevant when you're closer to 0.
Oh, maybe. Though like maybe, but we also know that it's like hard to tell if you're close to identity with it. Like still you have this like inverse 1 over poly. Like it's still like somehow it's still hard to decide between inverse 1 over poly error if you're like if you're trying to decide, let's say, am I identity or am I like greater than 1 over poly away? Okay, wait, this is a good question, because that problem is like co-QMA hard, which is like probably not easy, but okay, yeah, maybe it means that like detecting if you're closer to identity is easy, but okay, yeah, sorry, I'm not sure. Now I'm confused.
Thanks.
Yeah.
Any other questions? We have time maybe for one quick question. If not, then this is the end of the session. I encourage you to go to the other tracks because I think there is still a talk there each. And let's thank Natalie and all the other speakers of this session again.